Hello everyone. The title of this video is Factoring a Difference of Squares. Every exercise, every example I'm going to be doing in this video is taken directly from a free online textbook at openstax.org, and I'm in their algebra and trigonometry text in section 1.5, factoring polynomials. And I'm working under the heading, the objective, factoring a difference of squares. Alright, so as I said, all the examples are taken either from the examples in this text, or the try it problems, or from some of the even numbered exercises at the end of the section that are related to this particular objective. I will also have timestamps for each example in the description of the video below, in case you want to use those, bounce around a bit. And I also request that when I start a new question, pause the video and try to work it out yourself first before watching me do it and compare. Because if you're just watching me do these things and not practicing yourself, chances are you're not going to learn all that much. Alright, so the first example I have written out here, I have all my examples written out on paper. So again, we're just asked to factor the polynomial completely. And I'll say this out loud, I'm not going to write it, but when you're asked to factor a polynomial or factor any expression, the first thing you should look out for is the greatest common factor of all the terms, right? Find the GCF of all the terms and pull that out. Alright, but for the most part, we're going to be looking at polynomials where the greatest common factor of all the terms is 1. Right, so we won't have to pull anything out too much. Alright, so first here we have 81y squared minus 100. Now, this is a quadratic polynomial. Right, you have the highest power on the variable as the second power. There's a constant term here, and this is a quadratic. Like a times x squared plus b times x plus c, but instead of the variable being x, it's y. So that means we can try to factor it with that grouping method, or the AC method. Right, so that means we can try factoring by grouping. Or that AC method, whatever you've heard it called. In this particular text, it's grouping method. Right, because we can think of 81y squared minus 100 as 81y squared plus 0y to the first. That adding 0 of something it doesn't change the value of the expression. And then minus 100. So you see it's in that particular form. Quadratic term plus linear term plus constant term. And then I try the a times c, or grouping method, right? That would be the lead coefficient, 81, multiplied by negative 100, right? The constant term. And this is, negative 8100. And then I think of a pair of factors. Right, what's a pair of factors of negative 8100 that add up to b, that add up to 0, the linear coefficient? And that would be negative 90 and positive 90. Right. And remember, if this pair of factors of AC that add up to b, if this pair of factors cannot be found, then the polynomial is not factorable over the integers. Right? It's prime. But I could find them. Right? Negative 90 times 90 is negative 8100. Negative 90 plus is 0. Right? And then you use this pair of factors to rewrite the middle term. Right, so this is 81y squared, and then instead of plus 0y, I'm going to write it as minus 90y plus 90y, right, using the minus 90 and positive 90. And then we have the constant term, minus 100. And then here comes the grouping part, right, where I break these into two groups of 2. Right, in the first set of parentheses, the first group, I put the first two terms, 81y squared minus 90y, plus, and then in the set of parentheses, I put the next two terms, 90y minus 100. Right, then you factored each group separately, pulled the greatest common factor out of each group separately. So the first group, the greatest common factor of these two terms is 9y. And if I factor out 9y, what I'm left with is 9y minus 10. Okay, and then from the next group, right, plus, we have 90y minus 100. The greatest common factor is 10. Pull out a 10, and I'm left with the same remaining factor, 9y minus 10. And then you see we have 9y minus 10 in common in both of these. So this would be 9y minus 10 multiplied by, the factor remaining when I remove 9y minus 10, which would be 9y plus 10. And there you go. That's the factorization of our original expression. Right? 81y squared minus 100 is equivalent to 9y minus 10 times 9y plus 10. And of course, don't forget to check your work. I'll do it after, though. Right? I'll do it after we talk about a difference of squares. Right? Because again, you can always do this with a quadratic polynomial. You can always try this grouping method that I showed you here, right? And I've showed this in previous videos as well. Now that takes a bit, though, right? If a polynomial has two terms, right? Notice that this polynomial has two terms. It might be, and it's a difference, right? It's two terms, and it's a difference, right? Minus subtraction. It might be a difference of squares. Let's see. Right? So here's a difference of squares over here. So a difference of squares is any expression that takes on the following form, where you have some expression, to the second power. You have one perfect square minus, right, it's a difference, and then another expression to the second power, right, another perfect square. If you ever come across an expression like this, you can easily factor it. This is equal to the product of a minus b times a plus b. Right, and this a minus b and a plus b, these are called conjugates, binomial conjugates. Binomial because they have two terms each, and conjugates is just from they have the same terms but with a different sign in the middle, right? A plus b, a minus b. Still have a and b as the two terms, but with a plus and a minus in the middle. That's the only difference. So this is the difference of squares, formula, if you want to call it that. All right, let's take a look at our example here. Right. So we have 81y squared minus 100. And you might recognize, hey, this is a square. 81 is a perfect square too. 81y squared you can express as 9y to the second power, right? 9y times 9y is 81y squared. and then we have minus, right? Then we have a difference, and then 100 is 10 squared. So I have a difference of squares here, a difference of 2 squares. And if you think of the 9y as the capital A in my little formula, and think of the 10 as capital B in the formula, then we should easily, again, if you recognize that you have a difference of squares, you can then easily factor this, write it as a product. And it's going to be, now it can be a minus b times a plus b, or a plus b times a minus b, right? The order that the factors in doesn't matter. So a 9y minus b, so 9y minus 10 is a factor, times a, which is 9y here, plus b, right, plus 10. So there's your a minus b times your a plus b, right? Just filling in for a and b, 9y and 10 respectively in the formula. And there you go. And you see that this is exactly the same thing I got when doing it the long way, right? Doing it with that grouping method. 9y minus 10 times 9y plus 10, or 9y plus 10 times 9y minus 10, it doesn't matter. Wonderful. Alright, so now that I've factored, let's check it. You should always check your solutions. Don't forget that, when you check, you're factoring, you're multiplying. Right? You multiply these two factors and see if you get the original expression back, 81y squared minus 100. Well, let's see. So I'm going to take the 9y minus 10 times the 9y plus 10, and remember how to multiply polynomials. You take you can only multiply 2 at a time, which I have here, 2 factors, and you take every term from one and distribute to the other factor, and then combine like terms after. So first I'll distribute the 9y. Right, so 9y times 9y, that's 81y squared. Then 9y times positive 10 would be positive 90y. Alright, now I'm done with the 9y. Move over to the negative 10. Distribute the negative 10. Negative 10 times 9y is negative 90y. And then negative 10 times positive 10 is negative 100. And then look, the 90y and negative 90y become 0y. They go away. And I'm left with 81y squared minus 100, which is exactly the same as the original expression. Right? And that's what you're looking for when you check your factoring. Right? If you multiply your result and get the original expression back, and you know that you actually multiplied correctly, then your factorization is a good factorization. And then one other thing I've been pointing out in these videos is that when you say that two expressions are equal, I say that 81y squared minus 100 is equal to 9y minus 10 times 9y plus 10. Another way to kind of test this out, it's not a way to prove that they're equal, but just a test to see if you believe they're equal, is replace the variables with numbers and see, this expression and this expression should have the same value no matter what you plug in for y. Right? When I plug in 0 for y, both of these expressions should end up giving you negative 100. When you plug in 1 for y, both of these expressions should end up giving you negative 19, and so on. Right? You could plug in anything for y, and the values of these expressions should match. And I want to show you, a few values. I'm going to go to a free online graphing calculator at desmos.com, and I'm going to enter these expressions. We had 81y squared minus 100. Now here's the issue with this though. See, it comes up. See that? Try adding x equals. Don't feel like doing that. See, x's and y's are a tricky thing in this Desmos because you have the x-axis and y-axis over here. So x means something on the x-axis, y means something on the y-axis. So what I'm going to do instead is I'm going to change y to just another variable a and add a slider for a so we can change the value of a. See that? So when a is negative 5.3, 81a squared minus 100 is 2175.29. When a is 4.2, there's the value. All right. And then below this, I'm going to enter our factorization. Right? We had 9, instead of 9y minus 10 times 9y plus 10, I'm going to do 9a. I'm going to replace y with a. 9a minus 10 times 9a plus 10. And look, see, they have the same exact value for the same value of a, and they'll always have. You can change the value of a to whatever you want, and these expressions have the same value every single time. All right, now this only goes from negative 10 to 10. I mean, you can change this and have it go from negative, whatever you want to whatever you want, negative 59 to 72, and have this, the steps be every unit. And then you see changing the value of a doesn't matter. They always have the same value. Okay. All right, so let me clear these away and go back to our paper. But yeah, you should always be checking, you're double checking your solutions though. Make sure you're doing things right. Great. All right, so the next examples I'm just going to treat as a difference of squares. Every single example we're given in this video is in this form, this a squared minus b squared. Now again, if it's a quadratic, you could do this grouping method. It's not wrong, not impossible. It's just, when there are two terms and it's a difference, hopefully recognizing it as a difference of squares will make things much quicker. So for number 2, you have 25y squared minus 196. Again, you could do this with the plus 0y in the middle. Take 25 times negative 196, then try to find factors of that that add up to 0, and then use the grouping method. So it's not impossible. Right? You can do it that way. But I have two terms. It's a difference. Right? So this, and there's a square here, so this may be a difference of squares. Let's see. 25y squared, that's 5y to the second power. Right? 5y times 5y is 25y squared. So the first term is a perfect square. And then we're subtracting, and then 196, and I hope you know some perfect squares. 196 is 14 squared. And you can double check that. Take 14 times 14. All right, that's 196, I promise you. So I have a difference of squares. Right? And I'm going to consider the 5y as the a from earlier, from the little formula I wrote, and 14 as the b. So this will factor, remember, to a minus b or a plus b. It doesn't matter what order you do it, but I like doing the minus first for some reason because it's already there, right? So the first factor, 5y minus 14 times, and then the second factor, a plus b, 5y plus 14. And there you have it. There's our original expression factored. written as a product. And once again, please, and I'm only going to do that for that first problem, remember to check your work. All right, multiply these, see that you get 25y squared minus 196 back. Also, if you want to test some values out, this expression and this expression should have the same value no matter what you plug in for y. Or if you want to change y to some other variable like I did in the Desmos, you can do that too. Great, pretty easy stuff once you got the hang of it, once you recognize something as a difference of squares. So number 3, again I got two terms. There's a difference, right, subtraction, and there's a square, so there's a good chance that this is a difference of squares as well. 4m squared, that's 2m to the second power, right? 2m times 2m is 4m squared. Minus, and then another square, 9. 9 is 3 squared. So I got a difference of squares. Again, I'm going to think of the 2m as that capital A, and I'm going to think of the 3 as the capital B, and then we factor the a minus b times a plus b. 2m minus 3 times a plus b, 2m plus 3. And there you go. Done. And again, please don't forget, and I'll try to remember to write this every time, don't forget to check your work. Multiply these, make sure you get the original expression back. Also, you could try verifying that these have the same value no matter what you replace m with. Right, they should have the same value if they are truly equal. Great, I got just one more of these. And then I have a little warning for you at the end. A common mistake that people make when a polynomial has two terms and a square. So number 4, 324x squared minus 121. Again, there are two terms. It's a difference, right? You're subtracting. There's a square, so there's a good chance that this is a difference of squares. Now 324 is 18 squared. Again, I'm hoping you know some perfect squares, at least up to 20. I would recommend learning those. 18 times 18 is 324. So 324x squared is 18x to the second power, right? 18x times 18x. So the first term's a perfect square, then minus, right? And then 121 is 11 squared. Another nice integer square, perfect square. Alright, so I'm going to think of 18x as A, and think of 11 as B, and then this factors to a minus b times a plus b, or a plus b times a minus b, whichever order you prefer. So a minus b would be 18x minus 11 times, and then a plus b, 18x plus 11. And there we go. Completely factored. Written as a product. And don't forget to check this work. Multiply these together, combine like terms and all that, and you should get the original expression back. Also, you might want to verify that, these take on the same value no matter what you plug in for x. Alright, now here's a warning for you. We've seen a bunch of factorizations of the difference of two squares. A sum of two squares. A sum of two squares does not factor over the integers. does not factor over the integers. When I say over the integers, right, what I mean is you can't factor it and still have all the coefficients be integers, right? You know, here when I factored this polynomial, see all the factors still had integer coefficients, 18, negative 11, 18, and positive 11. So that's what it means to factor over the integers. So a squared, right, plus b squared does not factor over the integers. Right, for example, you know, x squared plus 9. This is x squared plus 3 squared, right? It is a sum of squares. And because of that, does not factor over the integers. We would say that this was a prime polynomial, a prime quadratic, does not break down any further. All right, now it is factorable over the complex numbers, but we're not going to talk about that junk for a while. Okay, so just be aware. You were only really going to be able to factor differences of squares, not sums of squares. Please, please, please get that in your head. Great. All right, so I'm hoping that watching me go through, just these 4 examples, it wasn't too much, but I hope watching these 4 examples, these 4 questions, helps you in some way when you're asked to factor a difference of squares on your own. And thank you very much for watching.